Okay, so lecture notes on number theory. So multiplication is trickier than you'd think, and so we're going to look at multiplication a little bit in terms of division and multiplication. And we're dealing with positive integers here. So A divides B means, is usually written this, A divides B, you can think of it as A divides B like that. If there's some other positive integer C, so that A times C, A divides B. Sorry, A divides B is B over A. So A times C equals B, right? So this should be equal to some integer, A times C equals B. Unfortunately, yeah, this notation is kind of backwards. A prime number is a number that's got no other divisors besides one in itself. And we're still dealing with positive integers here. So another way to state divisibility is that A divides B if the remainder of B when you divide it by A is equal to 0. So we're going to introduce some notation here. B is equivalent to R mod A, means that the remainder of B when divided by A is some number R, and R is between 0 and A. And the use of this symbol should tell you that there's an equivalence relation lurking in the background here. So 10 mod 2 equals what? Well, this is asking for the remainder of 10 when divided by 2. But 10 over 2 equals 5 exactly. Or 10 can be written as 2 times 5 plus 0. That's my remainder. So 10 mod 2 equals 0 because there's a remainder of 0. What about 10 mod 4 equals what? So again, we want the remainder of 10 when divided by 4. Now 10 divided by 4 is 2 with a remainder of 2, or 10 equals 2 times 4 plus 2, because 2 times 4 is 8. So there's my remainder. It's a remainder of 2. So 2 does divide 10 because you get a remainder of 0. 4 does not divide 10 because there's a remainder of 2. Okay. So prime numbers are the building blocks of integers. We want to be able to tell if an integer is prime. So is 587 prime? How do we go about telling that? Well, we want to know what the square root of 587 is. And the square root of 587 is 24 point something, something, something. Now, why are we interested in the square root of 87? Well, if I multiply two numbers together to 587, if they're both less than square root of 587, then their product will be less than the square root of 587 times the square root of 587, which equals to 587, right? So if we multiply two integers together to get 587, they can't both be less than square root of 587. Likewise, they can't both be greater than the square root of 587. So if the product of two integers is 587, one of them has to be less than or equal to square root of 587. And this should be m. So one of them is less than square root of 587, the other one is greater than 587. As an example, think about 10. Square root of 10 equals 3. So if two numbers multiply together to give you 10, one of them's got to be bigger than 3, and one of them's got to be, well, 3 point something something. One of them's got to be bigger than 10, and one has to be, if two integers multiply together to give you 10, one has to be bigger than 3, one has to be less than 3. So 10 equals 2 times 5, less than 3, bigger than 3. 10 equals 1 times 10, less than 3, bigger than 3. So that's nice, because if we want to find out whether or not 587 is prime, we want to know, can we divide a prime number into it? We only have to check up to square root of 587, though. So what prime numbers do we have that are less than 24, 2, 3, 5, 7, 11, 13, 17, 19, 23? We can divide 587 by these numbers. So 587 divided by 2 gives me 293 with a remainder of 1. 587 divided by 3 is 195 with a remainder of 2. 117 when we divide by 5 with a remainder of 2. 83 with a remainder of 6. Notice that when we take 587 and we divide it by these numbers, the quotients are going down as the divisor 235 goes up. So 7 times 83 is close to 587, but you get a remainder of 6. 11 is 53 with a remainder of 4. 45 with a remainder of 2. So 587 divided by 13 is 45 with a remainder of 2. 17, 34 with a remainder of 9. 30 with a remainder of 17. And 23 divided by 587 divided by 23 is 25 with a remainder of 12. And we can go on to 29, for example. Oops, 29 goes here. And then that gives me 20 with a remainder of 7. Note that once we go past the square root of 587, right? 23 times 25, but then 29 times 20, right? That number is less than the square root of 587. So the answer to this question is no. No primes divide 587, and we don't need to check anymore because if a prime number that was bigger than square root of 587 divided 587, then it would be multiplied by one of these numbers that are less than the square root, and we already know none of those numbers divided. So that's how to check if a number is prime. Let n be a positive integer. If every prime with p less than the square root of n does not divide n, then n is prime. So prime numbers are the building blocks of positive integers because every positive integer can be decomposed into a product of prime numbers. We can find the greatest common divisor, which is the biggest number that divides both of them, and the least common multiple is the smallest number that both of them divide. So 1326 and 583. How can we find the prime factorization of this? Well, this is an even number, 1326, so we know it's divisible by 2. And we can do that division. That gives me 663 times 2. 663 is odd, so not divisible by 2, but the numbers 6 plus 6 plus 3, that adds up to 15, which is divisible by 3. So we know there's a factor of 3 floating around. And that gives me 221. So I need to factor 221. I know that the square root of 221 is about 14. So I only need to check primes up to 14, namely 2, 3, 5, 7, and 11 to see if any of those, and 13, to see if any of those divide 221. We know 2 doesn't because 221 is odd. We know 3 doesn't because 2 plus 2 plus 1 is 5. We know the 5 doesn't because it doesn't end in a 0 or 5. 7, you actually have to go and do a division. You find that it doesn't divide by 7. Divided by 221 by 11, you find that there's a remainder. But 221 divided by 13 does work. And that's that. Great. What about 5083? If we want to factor this, how many things do we have to look at? Well, we know that it's not divisible by 2 because it's odd. We know it's not divisible by 3 because 3 plus 8 plus 5 is 16. And we know it's not divisible by 5 because it doesn't end in a 0 or a 5. So that means we're going to have to look at more prime numbers. What's the square root of 5083? That's about 71. So technically we have to check all the prime numbers up to 71 to see if they divide 5083. we can list out a bunch of them, at least the first 5 tens, 2, 3, 5, 7, 11, 13, let's see, 1, 2, 3, 4, 5, 6, 17, 19, 23, and then 29. I think of the first 10, and then there's some more after that. So we'll just start thinking about, is this number divisible by any of these primes? We know it's not divisible by 2. We know it's not divisible by 3. We know it's not divisible by 5. And then the rest, you just have to start checking them. It's not divisible by 7. It's not divisible by 11. It is divisible by 13, though. And so we take 5083, factor out of 13, and that gives me 391. Great. So now we need to factor 391, but that means we only have to look at numbers up to the square root of 391, which is 19. So we don't have to look at 23 or 29 because one of these other ones ought to have divided that. And we check 2, 3, 5, 7, and 11, right? If they don't divide 5083, they're not going to divide 391, because if they divided 391, they would have divided 5083. So we just have to go forward with 13, 17, and 19. 13 doesn't divide it, but 17 does. And there we go. We've got these things factored out. 1326, oops, 1326 is 2 times 3 times 13 times 17. 5083 is 13 times 17 times 19. Now, the greatest common divisor is the biggest number that divides both of them. It's the biggest number that's a factor of both of them. The factors are just multiplications of the primes. So what are the factors of 5083? Well, 13, 17, 19, those are all factors. 13 times 17 is a factor. 13 times 19 is a factor. 17 times 19 is a factor. So what's the biggest factor that shows up in both of them? Well, it's the 13 times 17. That's the greatest common divisor. And that is some number, 221. So that's the biggest factor of both numbers. The least common multiple is, what's the biggest number that has, what's the smallest number that has both of these two numbers, 1326 and 5083, as factors? Well, if you're going to be divisible by 1326, you have to have all of these factors. So whatever the number this is, it's got to have that, because this is 1326, that's one factor. And then I've already got a 13 and 17 written down. I just need to throw in a 19. And that makes this 5083, right? So 5083 is a factor, 1326 is a factor of this number, which is apparently a number that I didn't bother actually multiplying out. But it should be 1326 times 19, which is 25,194. And the last thing we want to note here is that the greatest common divisor times the least common multiple will actually be equal to the product of the two numbers themselves, right? Because if I took this and multiplied it by this, what I'm doing is I'm going to get 1326, that'll be this part, times 19 times 13 times 17, which is 5083. So the least common multiple and the greatest common divisor are related to in that way. We're not really interested in least common multiple much, but we will look at the greatest common divisors. There are other ways to find greatest common divisors besides doing the factorizations. This is very expensive, right? Because you have to check all these numbers. The Euclidean algorithm is a very useful trick to finding the prime factorization without actually doing the not finding the prime factorization, finding the greatest common divisor without doing the prime factorization. So a and n are positive integers. R is the remainder of a when divided by n, so that a is equal to r mod n. Then the greatest common divisor of a and n is the greatest common divisor of n and r. N and r. So what does this statement mean? That means that there is some, and everything's a positive integer here, right? So some positive integer usually called q for quotient with a equals r times q plus n. Right? So if we're using 8 and 28, we know that 28 is, oh, I got it backwards, n times q plus r for remainder. So 28 would be 8 times 3 plus 4, right? This is my number q. So if some number, we'll call it t, divides a and n, right? Then t divides a minus nq, which equals r. And remember that divides here means divides without leaving a remainder. So if t divides these two things, then it has to divide these two things because this is a and this is n, right? It divides both of those terms, but a minus nq is r, so t divides r, and also n, right? If t divides, we can do the same thing really now by saying, suppose we look at n and r, n and r, then t divides a, which is n times q plus r, right? Because t divides this and t divides that. So t divides a. And what's the upshot then? Any number that divides a and n also divides r and also n. Any number that divides n and r divides a and also n. So the set of divisors of a and n, the set, so squiggly braces, equals the divisors of n and r. Right? So any number that divides these two also has to divide these two and vice versa. But the biggest one in this is the greatest common divisor of a and n. The biggest one in this is the greatest common divisor of n and r. And so therefore, the greatest common divisor of a and n has to be equal to the greatest common divisor of n and r. So here, a and n are 8 and 28. So the greatest common divisor of 8 and 28 is 4. The greatest common divisor of 8 and 4 is also 4, and those have to be equal to each other. Okay, so that's what makes the Euclidean algorithm go. And we'll show this here in example 5 about exactly how we go about doing this. And if you're in class, last week you saw this. So Euclidean algorithm to find this. So we can divide 5083 by 1326, and we get 3 times 1326 plus 1105, right? And this is my remainder. It has to be between 0 and 1326. Great. What's the next step we do? We take before I do that, so let's note that the greatest common divisor of 1326 and 5083, which is what we're looking for, has to now be the greatest common divisor of 1326 and 1105. because of the previous statement. So 1326 equals what in terms of 1105? So we divide 1326 by 1105. Remember, this is integer division, not decimal division, right? So we don't want any decimals, we want remainders. And if you actually do that, you get 1 times 1105 plus 221. That tells me now that this is equal to the greatest common divisor of 1105 and 221. Right? The greatest common divisor of this and this is the same thing as greatest common divisor of this and this. 1105, move the 1105 over, equals, I'll divide by the new remainder, which is 221, and you get 5 times plus 0. Great, so 221 divides 1105. It's also the biggest number that divides 221. Right? The biggest number that divides 221 is 221. So the greatest common divisor of these two is 221. Well, that's the same as the greatest common divisor of these two, which is the same as the greatest common divisor of those two. And I believe that's the same number we got up here when we found the greatest common divisor of 1326 and 5083 through prime factorization. So this doesn't give you the prime factorization, but it does give you the greatest common divisor, and it does it pretty quickly. Here's only 3 steps, and the steps are all basically subtraction, right? How do you actually find this remainder? Well, 5083 divided by 1326, if you use a calculator, it's 3 point something something. So you take 5083 minus 3.3 times 1326, and that'll give you the remainder of 1105. So the same thing here. What's the greatest common divisor of 161 and 112? Well, 161 is 1 times 112 plus 49. And so that tells me that the greatest common divisor of 161 and 112 is actually equal to the greatest common divisor of 112 and 49. So move things over. 112 is something times 49 plus something else. And that's going to be 2 times 49 because that's 98 plus 14. So this is going to be the greatest common divisor of 49 and 14. And you can tell right now that that's going to turn out to be 7, but let's finish out the procedure. 49 equals something times 14 plus a remainder. And this something is 3 times 14 because that's 42 plus 7. So this equals the greatest common divisor of 14 and 7. And then we finish this off. We move the 14 over, 7 over, 14 equals 2 times 7 plus 0. Right? Greatest common divisor of 7 is 7, and that divides 14, right? That's what we have here. 14 is 2 times 7. And so the greatest common divisor of 161 and 112 is 7. We haven't factored these numbers, but we did find out the greatest common divisor, and all it takes is subtraction. So a nice thing about the Euclidean algorithm is that you can reverse the Euclidean algorithm, and this is a useful thing because this gets us to the root of some encryption things. So if a and b are positive integers, there are going to be 2 other integers, s and t, so that s times a plus t times b equals the greatest common divisor of the 2. So how do we go about doing this? We want to find s and t so that this is true. So what I'm going to do is I'm going to take my Euclidean algorithm from example 5, which is this. Sorry, 1326 plus 1105. 1326 equals 1 times 1105 plus 221. So that gets me all the way down to 221. I want to find an equation where 221, that's my remainder, is equal to something times these 2 numbers. right? Something times 1326 plus something times 5083. And the connection is then I can use this 1105 to sort of work my way through this. So what I'm going to do is I'm going to rewrite everything in terms of my remainders. So take this and rewrite it as 1105, which is my remainder, equals 5083 minus 3 times 1326, and 221 equals 1326 minus 1105. So there's my 221. I want that to be equal to something. So I need to find a way to get rid of the 1105 because I don't want the 1105, but I want to have a 5083 and a 1326 in it. So what can I do? Well, I know that 1105 is equal to all of this. So I'll just replace this 1105 here with that expression. And what do we get? 221 equals 1326 minus the quantity 5083 minus 3 times 1326. And 221 then is 1326 minus 5083 plus 3 times 1326. And finally, 221 is 4 times 1326 minus 5083. So what we get here is S equals 4 and T equals minus 1. Very important point here, note that we never multiply these things out. We're trying to keep track of these coefficients, the 3 and the 4. So don't multiply the 3 times the 1326 because then you lose your numbers a little bit. And these S's are going to become actually very important, and we want to know exactly what they are. So what about this? Find integers S and T. That's 7 equals 161S plus 111T, 112T. So what we know is the greatest common divisor of 161 and 112 is equal to, usually S is times the smaller one, 112, and then T is times the bigger one. Right? And we know what the greatest common divisor is because we worked that out. It's 7 should be 112S plus 161T. So I should have had these backwards. Okay. So how do we go about finding S and T? Well, again, we take our Euclidean algorithm from above. Which is this. We only need to go as far as we need to get to our greatest common divisor, which is 7. Rewrite each equation by isolating the remainder. 7, 14 equals 112 minus 2 times 49. 49 equals 161 minus 112. So here's our 161 and our 112 that we want 7 to be equal to. Here's a 7. How are we going to get that? Well, the 14 in this equation can be substituted in with these. And then all the 49s in this equation and this equation can be substituted in with this, and that will get us the 161 equals 112 equals 7. So 7 is equal to 49 minus 3 times the quantity, whatever 14 is equal to, which is this, 112 minus 2 times 49. We multiply that out, and actually all I'm doing is distributing the 3, but I'm not multiplying it into any of the remainders because I need to keep track of what the remainders are. Minus 3 times minus 2 is plus 6. So 7 equals, I've got a total of 6 plus 1, 7 times 49 minus 3 times 112. Okay, Now we can clear out the 49s by using that. 7 equals 7 times the quantity 161 minus 112, minus 3 times 112. 7 is 7 times 161 minus 7 times 112 minus 3 times 112. 7 equals 7 times 161 minus 10 times 112. So my S is minus 10 and my T is 7. So there we go. We've got integers T and S like that. Okay. Sometimes it's not too hard to actually figure out what these could be. Right? 5, 13 are both prime. So we know the greatest common divisor of 5 and 13 equals 1. 13 equals 1. So there should be two numbers, S and T, so that 5S plus 13T is the greatest common divisor of those two, which equals 1. And you can think about that a little bit and see, well, T equals minus 2, S equals 5 works. 1 equals 5 times 5 plus 13 times minus 2, right? No, actually, this wants to be the plus 2, and that's the minus 5, right? 26 minus 25 is 1. So, right, sometimes if you have small numbers, you can just look at it, but usually you need to run the Euclidean algorithm backwards. So this leads us to a discussion of remainders. So here's where our equivalence relation pops up. So define equivalence relation on the integers by n is equivalent to m. If and only if n minus m is divisible by 6, show that this is an equivalence relation and state the equivalence classes. So if x and y, if x is an integer, any integer, then x minus x equals 0, which is divisible by 6 because every number, 0 is divisible by every number except 0. So it's reflexive. Symmetric, suppose x minus y is divisible by 6. What that means is x minus y is 6 times k for some integer k. But then what do we have? Well, y minus x equals 6 times minus k, right? If you multiply both sides by minus 1, right, the left side becomes y minus x, the right side becomes 6 times minus k, but that tells me that y minus x is divisible by 6 because it's 6 times some integer. So it's symmetric, right? If x minus y is divisible by 6, so is y minus x. That's a y there. Transitive, suppose x minus y, y minus z, divisible by 6. What does that get me? Well, that tells me that x minus y plus y minus z is divisible by 6 because that's divisible by 6 and that's divisible by 6. But if the y's cancel out there, that's the same thing as saying x minus z is divisible by 6. So it's transitive, right? If x minus y, y minus z is divisible by 6, so is x minus z. So it's an equivalence relation. What are equivalence classes? Well, the equivalence class of 0 is all numbers that are equivalent to 0. So it's a big set. 0 is equivalent to 0, we did that. What's a positive number that's equivalent to 0? Well, 6, right? 1 is not equivalent to 0 because 1 minus 0 is not divisible by 6. 2 is not equivalent to 0 because 2 minus 0 is not divisible by 6, ... But 6 is equivalent to 0. 12 is equivalent to 0. 18, ... Minus 6, minus 12, minus 18, ... What's the equivalence class of 1? That's going to be all numbers that, when you divide them by 6, all numbers that are, if you take the difference with 1 gives you something divisible by 6. So 1, 7, right? 7 minus 1 is 6. That's divisible by 6. So 7, 13. 13 minus 1 is 12. That's divisible by 6. 19, minus 5, minus 11, minus 17, Minus 5 minus 1 is minus 6. Minus 6 is divisible by 6. It's equivalence class of 2. You can see how this is going to go. This will be minus 16, minus 10, minus 4, 2, 9, 15, no, 14. No, this should be 8, 14, 20, Right? And so when you look at this, and you can figure out 3, 4, 5, 6, this is all numbers with remainder equal to 0 when divided by 6. This is all numbers that give you a remainder r equals 1 when divided by 6. This is all numbers that give you a remainder 2 when divided by 6. So if two numbers are in one equivalence class, and n and n prime are a different equivalence class, then m plus n and m prime plus n prime will be in the same equivalence class. So if m is in one equivalence class, suppose we have m is in the equivalence class with 2. What does that mean? M equals 6 times something, and we'll call it K1, plus 2. And suppose n is in the equivalence class of 5. What does that tell me? It tells me n is 6. I don't need K, I need a different letter, J1 plus 5. Right? So being in the equivalence class of 5 means you leave a remainder of 5 when you divide it by 6, so n has to be 6J1 plus 5. M and m prime are in the same equivalence class, so m prime will say is 6K2 plus 2. N prime will say is 6J2 plus 5. So this is equivalence class of 5, equivalence class of 2. So if we add m plus n, we get 6 times K1 plus J1 plus 7. M prime plus n prime would be 6 times K2 plus J2 plus 7. So m plus n is in the equivalence class of 1, and m prime plus n prime is in the equivalence class of 1, right? Because 1 and 7 are in the same equivalence class, so we'll just call that 1 there. Great. So what about if we multiply these things together? What's m times n? M times n is, well, you have to FOIL everything out. 6K1 times 6J1 is 36K1J1 plus 30 times K1 plus 12 times J1 plus 10. M prime times n prime is 36K2 times J2 plus 30 times K2 plus 12 times J2 plus 10. So this is the equivalence class of 4, right? Because what do you get when you divide 10 by 6? You get a remainder of 4. This is also in the equivalence class of 4. Note that this whole thing is divisible by 6, so it doesn't contribute to the remainder. Likewise, this is divisible by 6. 36, 30, and 12 all divisible by 6. So what's the upshot of this? You can add remainders and you can multiply remainders. And usually we just deal with the numbers 0, 1, 2, 3, 4, 5 as the remainders of 6. So we can do addition and multiplication mod 6, which is actually pretty straightforward. What's 0 plus any of these numbers? That's 0, 1, 2, 3, 4, 5. 1 plus number 1. 1 plus 1 is 2. 3, 4, 5. Now we have to be a little bit careful. 1 plus 5 equals 6. But what's the equivalence class that 6 is in? The equivalence class of 6 is the same equivalence class as 0. And so when we're doing addition with remainders, we want to only use the numbers between 0 and 5. So 1 plus 5 equals 6, but that's equivalent to 0. So we define that. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. 2 plus 4 is 6, but that's 0. 2 plus 5 is 7, which is 1 more than 6, so we give that a 1. 3, 4, 5. 3 plus 3 is 6, that's a 0. 3 plus 4 is 7. 7 is 1 more than 6, so we give that a 1. 3 plus 5 is 8, which is 2 more. And so you can see how this table will go. If you ever take algebra, advanced algebra, you'll see this table again when you get to groups. So there's addition. Multiplication is the same sort of thing. If you ever multiply by 0, you always get 0. Multiply by 1, you always get 1. No, if you multiply by 1, you always get the same thing back because it's the identity. 2 times 2 is 4. That's not too bad. 2 times 3 is 6, but 6 is equivalent to 0, so that's 0. 2 times 4 is 8, which is 2 more than 6, so that's 2. 2 times 5 is 10, and that's 4 more than 6, so that's 4. 3 times 2 is 6, that's 0. 3 times 3 is 9, which is 3 more than 6, so that becomes a 3. 3 times 4 is 12, which is a multiple of 6, so that's 0. 3 times 5 is 15, which is which is 3. It's 3 more than 12. What about 4? 4 times 2 is 8, which is 2 more than 6. 4 times 3 is 12, which is 0. 4 times 4 is 16, which is 4 more than 12. And then 4 times 5 is 20, which is 2 more than 18. 5 times 2 is 10, which is equivalent to 4. 5 times 3 is 15, which is equivalent to 3. 5 times 4 is 20, which is equivalent to 2. And then 5 times 5 is 25, which is 1 more than 24, which is equal to 6. So there is our multiplication table mod 6. And so A and B are inverses mod n if A times B equals 1 mod n. So what are the ones that have inverses mod 6? 1 times 1 equals 1, that's here. And 5 times 5 equals 1. That should be the equal sign. None of the other ones, right? There's no other ones in this table. So 2, 3, and 4 do not. So there's an important point to keep in mind in looking at this example. As soon as I figure out where my notes have gone. Right? The greatest common divisor of the numbers that have inverses with 6 is 1. The greatest common divisors of numbers that don't have inverses mod 6. When you look at the greatest common divisor of those numbers in 6, you get numbers that are not prime to it. And so in fact, having an inverse means the same thing, right? Multiplying, being able to multiply to give you 1 is the same thing as saying that the greatest common divisor is equal to 1. So if the greatest common divisor of A comma n equals 1, what do we know about that? We know that there are s and t, so that as plus nt equals 1, right? Integers s and t from the running the Euclidean algorithm backwards. But if we think about remainders, when divided by n, right? So we're looking at remainders mod n. We have, if we divide the left side by n, right? This whole expression means the remainder of as plus nt when divided by n, and that's equivalent to 1 mod n. Okay, but that's just 1, and I'm going to leave off the mod n because the remainder is 1. This, we can use some of the rules that we had up above. If we're adding them, we can take the remainders of the two things first. And then when we multiply, you can take the remainder of each thing first and then multiply. This is 0, because when n is divided by n, you get a remainder of 0. So what do we get? A mod n times s mod n is equivalent to 1. And so A and S are your inverses. And that's why it's important to find this S when we're using the Euclidean algorithm, right? Run the Euclidean algorithm backwards and you can figure out what your S is. So we found out above that GCD of 112 and 161 equals 7. So no inverse, because the greatest common divisor of 112 and 161 is not 1. GCD of 5 and 13 equals 1. So there is a remainder. So there is, sorry, not a remainder, there is an inverse. How do we find it? Well, we found 5 times minus 5 plus 13 times 2 is equal to 1. So if we're thinking mod 13, inverse of 5 is minus 5, but we don't want to use numbers with negative numbers. We want to use numbers only between 0 and 12. And so minus 5, mod 13, minus 5 is equivalent to 8 mod 13, because minus 5 plus 13 is 8. So 8 is the inverse. How do we check that? Well, 8 times 5 should be equivalent to 1 mod 13. We know that 8 times 5 is 40. And that's 3 times 13 plus 1. The remainder when I divide 8 times 5 by 13 is 1. So 8 times 5 are inverses. Okay. Does 182 have an inverse mod 200? The answer is no. They're both even, semicolon. So the greatest common divisor of 182 and 200 is greater than 1. It's got to be at least 2. So no inverse. Does 173 have an inverse mod 200? Well, if the greatest common divisor of 173 and 200 is 1, then yeah. But we know that 200, right? 200 is 8 quarters. So it's 8 times 25, 2 cubed times 5 squared. Neither 2 nor 5 divides 173 because it's an odd number that doesn't end in 5 or 0. So the greatest common divisor of 173 and 200 has to be 1, right? And so that means that we can find an inverse to 173 mod 200. And how do we go about doing that? We run the Euclidean algorithm. So 200 equals 173 plus 27. 173 equals 6 times 27 plus 11. 27 is 2 times 11 plus 5. 11 is 2 times 5 plus 1. So there's our Euclidean algorithm. There's our greatest common divisor. How do we find my inverse? Well, again, we rewrite our Euclidean algorithm as in terms of the remainders. So, and then we start plugging back in. 1 equals 11 minus 2 times 5. 5 we get from here. So 1 equals 11 minus 2 times 27 minus 2 times 11. So how many 11s do I've got? I've got 1 here plus 4 more. So that's 5 times 11 minus 2 times 27. 11 we get from there. 1 equals 5 times 173 minus 6 times 27 minus 2 times 27. So I've got 5 times 173. 5 times 6 is 30, minus 2 more, so minus 32 times 27. And now I want to get rid of the 27s. So I have 1 equals 5 times 173 minus 32 times 200 minus 173, because this 27 we get from up here. So how many 173s do I have? I have 32 plus 5, which is 37 times 173 minus 32 times 200. So inverse of 173 mod 200 is 37, that number. Great. So what does this have to do with encryption? So this is just going to be a little run through about how Rsa encryption works. So suppose I have an integer, I want to encrypt it and send it to someone else and have them decode it. How can I do this? And why would you want to send integers? You want to send integers because any string of letters can be turned into an integer. We did a Huffman code early in the course, and that takes letters, turns them into integers, binary integers, in fact. So any string of letters can be turned into an integer. Rsa encryption tells me that prime factorization, prime factorization takes forever. And so, especially if you have very large primes that you have to factor out. So what Rsa encryption does is the recipient, right? Suppose you want to send me a message, I'm the recipient. So I pick 2 large primes, P and Q, ideally with, a billion digits in them, and you can go and look online for very large primes. You calculate Z equals P times Q. I do, the recipient, the person who's receiving the message. And then I calculate phi equals P minus 1 times Q minus 1. I keep that number private, that's important. So I pick n, some number n with greatest common divisor of n and phi equals to 1, which means that n has an inverse mod phi. And then I find the inverse of n mod phi. N and Z are made public, so the public knows that, and the public knows this n, right? But all you know about n is that it's some number that's relatively prime to some phi. There's lots of numbers. And you know Z, but if Z is a product of 2 primes, boy, that's going to take a long time to factor. It's a long time to figure out what Z is if both P and Q have billion digits. So that's my public key. So a sender wants to send an integer to the recipient. So you want to send me the letter A, whatever it is, that's your encoded thing. You need to have A to be less than Z, right? Which is why P and Q have to be big, because if you want to send a long message, right, you can only send as many digits as P times Q. But you can always break it up, I guess, if you're actually doing it. So what does the sender do? The sender calculates A to the n mod Z. Remember that A is the message, n and Z are my public key. So you calculate A times itself n times, and then take the remainder relative to this very large number, and you ship that off to me. When I get that, I take the inverse of n, take your message, coded message, raise it to that power, and take it mod z, and that should give me back your original message, which is the neat thing about this. So for example, we'll take p equals 5 and q equals 7. Right? So they're not very big numbers here, and that's because it's a little example. So z is p times q equals 35. Phi is 4 times 6, because it's 1 minus p minus 1 and q minus 1. That's 24. I'll take n to be 11. It's a nice prime number, and it's relatively prime to 24. So public, make public my key, which is 35 and 11. And then I calculate the inverse to n mod phi, and that turns out to be 11 as well, right, if you do a little bit of work. So this is private, and this is private. The other two numbers are made public. So the sender wants to send a equals 18. That's the message. We want to encode that. So we say, okay, we'll take 18 raised to the n, which is 11, mod 35, right? So 18 raised to the power 11 mod 35, which means take 18, raise it to the 11th power, and find the remainder when you divide it by 35. If you're actually doing this, there's a website called Wolfram Alpha. You should use that, right? But that turns out to be 2. So what you sent me is 2. I want to decode it. So I'll take 2 and I'll raise it to the inverse, which is 11, and take that mod 35. That will turn out to be 18. It's very slick, right? And he uses these inverses of these things. So that is the end of this video. I can just figure out how to stop recording.